All right, so in summary, these are project-specific inputs, AADT, that is equal to ADT times percentage GB. For axle load configuration, lateral wander, wheelbase, these are typical values are used. So vehicle class distribution growth, axle per truck, monthly and hourly adjustment factors, and axle load spectra. All these are, typical regional values are used, and you can use a software called PrepMe, to come up with these, or you can do it yourself. All right, so a quick case study that is probably useful to mention. That's why I put them in here. So Saudi Arabia, Kingdom of Saudi, or KSA is Kingdom of Saudi Arabia. They asked me to do a traffic analysis based on a very limited data that they had, not a weighing motion station. So they said, okay, this is all data that I can give you. Can you come up with some of the inputs for pavement ME? So what they gave me was 15 different classes of vehicles, and there was a classified count. So for each of these classes, so classes 1 through 15 are these. They look like these trucks, and they were counted for at certain roads. The Excel sheet was much bigger, but let's say in February, March, April, so this class was seen about 19,000 of them on those roads, on that particular road, I think. 20,000, 13,000, 4,700. So these are the number of times they have seen this. So you can see this is the table. So the challenge was, how do I use this? This is called classified count, and I come up with inputs, how many inputs I can come up with. So you can see there are a whole bunch of inputs. Let's see which ones I can get from that. From that, I can get vehicle class distribution and growth, monthly adjustment factors, axles per truck. All these I can get. Growth, I cannot get from that because that's only for 1 year, so we don't know what growth is going to be. So you have to somehow find another way of estimating the growth. And axle load spectra that you cannot get from that data. That's only classified count. You don't have the weight distribution. You need WIM data, weighing motion station data. And also these, you cannot get them, but they're not very important anyway, so you just need some average numbers, and I'm sure if you keep them, they're not going to affect the results. And we could not get hourly adjustment because I did not have an hourly distribution of those trucks. So I was able to get all these three, but not the other ones. Let's work on those. So what we had was, we had this total number of vehicles for each class. So what we need to do was, we needed to group these into these 10 classes of vehicles in pavement ME. So what we did is, if you look at, so classes 6 and 7, we mapped them, they are class 9, for example. This is an example. Why? Because there's a certain definition. If you have 5 axles, single trailer trucks, so that is considered as class 9. So if I look at here, this has 5 axles, 1, 2, 3, 4, 5. This also has 5 axles, 1, 2, 3, 4, 5. There are 5 axles, they're spaced a little bit differently. But 6 and 7, you have to group them into 9. So we call them, these two are 9. So we repeated the same procedure for others also, so based on this definition. And then we added them up. For class 9 trucks are summation of these two. This is how much, number of vehicles observed, and this is the percentage of vehicles. So that's where this came from. So 49.8 is this divided by the total number of vehicles from this data. So this is essentially percent distribution of each class. Are you with me so far here? Now, next, axles per truck. This is a bit challenging. So how do I do that? This is how we do this. So let's go back and look again for the classes 6 and 7. Now, first, you need to label the axles. So if you look at this, there is a single, and tridem. If you look at this, there are 2 singles, zero tandem, there's no tandem here, and one tridem axle, 2, 0, 1. So for this one. For this one, remember we are grouping these two into class 9. For this one, we have one single axle and two tandem axles. So this is how it is. Now, I came up with these numbers. How we come up with this number is here. It's described in Mepdg manual. 587.37 is the number of vehicles times 2 for this particular axle times 2 plus 7,000 times 1 divided by summation of these two. So I'm actually getting a weighted average of axles to come up with this 1.988. All right? So same procedure for the other one. So this times this plus this times this gives us the second one, 0.0024, and the third one, and these numbers go into this axles per truck. So it's not that difficult to get. Monthly adjustment. Now, this was the data that I showed you earlier. Now this is a group data. So we have the class, there were 15 classes, but so this is the original data. Now we mapped 6 and 7 to 9, 4 and 5 to 8. So we essentially add them up to have a smaller data. Essentially, class 8 is the summation of these two. Class 9 is summation of these two. So for each month, you have the number of vehicles based on these classes. So now, once you have this table, you have the total number of vehicles for each month and grand total of vehicles for all of them. So that's this table. You know, this table is here. The next slide is just moved up. So the way that we calculated, this is what's in Mepdg manual, is the truck for this one, for example, divided by the summation, total sum, multiplied by 12, will give you the percentage, essentially. Now, so it's very simple. This is equals to this, divided by summation of all this, multiplied by 12. So that's how you get the monthly distribution, and you have all these monthly distribution, and that's what this table goes into as 1.88, 1.15, and so on and so forth. And this is the monthly distribution for class 5. This is the monthly distribution for class 6. Class 7 didn't really exist in the data, so it doesn't really matter. And so on, so. Okay. Now, axle loads spectra is a bit more complicated, so this was not available in that particular example. And we talked about this being project specific. Okay, I think that's it. Now let's talk about climate inputs. Climate input is pretty straightforward. It's really, you just go here, climate station, and find the nearest climate station to your project. And when you click that, it will just load up the climate data, historical temperature, wind speed, sunshine, precipitation, humidity table. These are all already in Mepdg. It's ready to go. You don't really enter any number there. You just choose the location. That's pretty much it. So there's nothing much there to talk about. Okay, any questions about the inputs? Yes.
Could you go back to your monthly distribution?
Yes. Here.
I just want to look at that for a second, because it just seemed like really high for the 7s, I think.
For 7?
But I guess it makes sense, all right, because it's summing to 12. You just have like nothing in certain months. Just see,
yeah.
This looks odd.
It is odd because if you look at the raw data, 7 doesn't really exist at all.
It's just weird that it would just pop up in like 1 month.
Yeah, because it really what happens, it's, you know, the 7, it's rarely there's a truck that is classified as 7, and it might even be, yeah, very infrequent truck.
Years.
And I believe these are errors.
That's what I was going to
These
say.
are probably, the truck probably doesn't even exist.
Yeah.
It's just mixed with somebody else. And normally I would just put them all 0. But, you know, but it doesn't matter because if you look at the distribution, that's going to be probably a 0%. See?
Yeah.
So that's going to be 0% anyway, so it will never use that data. Okay. Okay, I think I'm done with this one. So let's move to let me close these so that I don't want anything. Okay. Now we're going to talk about calibration. Now, calibration of the models is a mandatory input for a mandatory step before use for actual pavement design. You can play with it, but you need to, for actual pavement design, you need to calibrate it. That's what's written here. Now, there's a calibration guide, local calibration guide. All the details are here. So I will be giving you a very brief, just an overview of what calibration. There are lots of details involved, but I'll be giving you an overview. And also there are some very useful references like jackknife testing and what this means on a TRB website about what calibration is. So out the box, Mepdg software comes with nationally calibrated models. Now, calibration validation of a performance prediction model is a mandatory step in their development to establish confidence in the design and analysis procedure and facilitate its acceptance as used. This is directly a quote from here. So it is really not optional, it's a mandatory step, okay? So that is why we do have in some of the countries outside the United States, and so there are some researchers, they use Mepdg, calibrated for United States, for nationally, and come up with a whole bunch of numbers and correction factors for Ashton-93 design based on nationally calibrated values. This is really wrong. You cannot do it. It's just wrong. You need to calibrate your pavement ME to the conditions of your country or state or wherever you live. Then you can do things like I mentioned. So calibration is important. What's calibration? Is the definition, a systematic process to eliminate any bias and minimize the residual errors between observed and measured results. What is cracking you measured in the field? Your pavement mean needs to be giving same numbers. That's the key. Now, when it comes to validation, once you calibrate, then you use a set of data that is not used in the calibration step. That's important. You need to set aside a whole bunch of data, field data, that is not used in the calibration step, and to validate the calibrated pavement ME. Okay? So this is called systematic process that re-examines the recalibrated model to determine if the design accuracy exists between the calibrated model and independent set of observed data. Now, we talked about these inputs. So one important thing is the calibration of these factors, beta 1, beta 2, beta 3, beta 4, there's no beta 4, there's beta 3 only. There's C1, C2 transfer function. There's the calibration of the material models, there's the calibration of the transfer function coefficients.